Today we will implement the Cartesian tree by implicit key. Let's remember what is Cartesian tree. So this is a tree which contains pairs of x and y, and it is a binary search tree by x and it is a heap by y. Here I assume that our x and y is unique. Also, we can say that if they have the unique pairs of x and y, we can say that the structure of a tree of a Cartesian tree is uniquely determined or defined. Okay. And what is Cartesian tree by implicit key? It is like a Cartesian tree, but we don't need to explicitly store the x and k. This k now stored in a tree structure. We can, using the tree structure, find the our xk. We don't need to store it. And also we store in every node a value itself and the size of the tree in every node. Also we can store some data to do querying on subintervals. So it's somehow like a static tree or a segment tree. We need to store the information about some subinterval. For example, we can store the sum of the subintervals, so the minimum or the maximum and so on. So actually any monoid. Okay, I do the videos about the Cartesian tree itself and about the segment tree. You can find them on the channel. Also, I will put these links to these videos in the source code. Let's start our implementation with the merge function. So, what we need? We need the binary tree definition here. We have this definition actually defined in this model, inside of this model, but it's defined like this. So it's either empty tree or a node with the left and right subtrees. Okay. And now let's go and define our merge function. What it do? It takes two trees, Cartesian trees with implicit k, and merge them into the one Cartesian tree with an implicit k. And let's write this in our type signature. So we have some binary tree, the first binary tree, and I need to provide a type here to define the node of this binary tree. And as I said, what we store in our node, we need to store the value itself, we need to store the size of the tree, and we need to store the if we want the query interval, do the query interval, we need to store the the query result on this interval, okay, which this tree represents. And also we need the monoid constraint for this last third element of the node, which store this querying value. So I can say that my binary tree contains this type A, which defined to me the size. So actually I can use the integer here for the size. I can use some type A for the stored value itself. It can be any type, so I don't need to define some concrete type here. And also I need some type B for my query result. And I need to say here that this is the monoid. Okay. This is the monoid. The B is monoid. Okay. Now I have a second tree of this exactly the same type, and then I merge them. I have the result itself, and of course this is it's represented as the same type. Now let's go to the function definition. We have this function. We have t1, t2, the trees which you want to merge, and they need to do the definition here. To do merging, we don't need any information about the value itself. Okay. We need only information about y, and I forgot this y in this type signature. So this means that actually I need to use I need to add this element inside my node. And I think I can do some more nice naming here. What if I define not B and like Q, like a query result here, to have more nice names. And A I will define it as a value itself. Okay. And last thing I need to define, I think this will be like integer. Or I can use I think I can do this more. I can define it as a y. So we have 4 elements here in every node, and this y must be must have the num type class. So I can use any num type to represent the. Actually, I don't need the num. I don't need a num here. I can use just ort. Okay, this is enough, because our y value is used to represent the heap property of our tree. So it's used to generate some random values, and it's used to balance our tree with good probability that our tree will be balanced. Okay, to do merging, at first I need to use the information about these y's. How we do merging? We actually take the tree with the maximum y. So we know that the structure of the Cartesian tree is uniquely defined, actually defined by these y's, and we take the maximum y and make it the root of our new constructed tree. And that's why I need a better match t1 and t2 here. So t1 can then better match as a node, and node contains some element which can be better matched. Actually, I need to know actually I don't need x, I don't need to know the size, but actually I think I need to know the size, because I need to reconstruct, I think I need to reconstruct the sizes. Actually, let's name this like size 1, value 1, and query 1, and y1. Okay. And we have left one subtree and right one subtree. Exactly the same thing we can do to tree 1. Oh, for tree 2, sorry. T2. It has s2, v2, query 2, and y2, and left 2 and right 2 subtrees. Now from here I think we go to some cases. We have two cases. When our y1 is greater than y2, we do one definition, and when our opposite case, when our y1 is less than y2, we do another definition. And I have no case, then they equal, because I assume that every y is unique here. Let's mark here that we also store y. Note. The first case, when y1 is greater than y2, this means that this node with a left subtree goes to our definition as it is. So this will be the new root. Also, what do we have here? We have here this right subtree and this all subtree. And we can merge them because everything here from the left must be less than everything here from the right. Yes, and we can use the merge function to recursively define our new right subtree. Okay, let's define it like this. Merge of R1 and root T2. Okay. The opposite case. What if our y2 is greater than y1? In this case, the new root is these three. Sorry, this node is a new root. Everything from the right subtree of this new merged tree we can define like R2. Of course, we need to define the left subtree here. And the left subtree is the merge of T1 and left 2. Okay, merge of T1 and left 2. I think like this. And we need to define the base cases of our recursion. Then we have empty trees. If we have empty trees, we can define our merge function like this. This is very obvious and very simple. If we merge something with the empty tree, this something is stay like it is. And this is the main logic, but one thing that we need to add here is to recalculate our new sizes. Actually, this is wrong values, and we need to provide some new some new here, new values. And also, of course, they need to provide some new values to our query results. Our values itself stay as it is, of course, and our y's stay as it is. They're not changed. Changed only the sizes of the trees and the query information. And let's do the definition. So we need S1, we need the new S1, new S2, and they need a new Q1 and new Q2. Okay. And of course, to calculate these new sizes, I need to extract some information from these new left and new right subtrees. And let's define it. Define this as new left tree. I defined it here. This is the new left tree. And I need to do a pattern matching here. So I need to extract this node information as new size. I don't need value. I need only new query here. And I don't need y. Okay. Okay. Now, how I defined S1, this new S1. I need to take this new S1 and add it to S1. So I take S1 and new S1. So size from this tree and size from the merged tree. Okay. And the Q1, what is the Q1? To calculate the new Q1, they need to have this Q1, this monoid, and using the append operation, we need to use this and Q1 here. Okay. And in the symmetric case, they defined our S2, new S2, as S2 plus new S2. And new Q2, we defined as Q2 and new Q2. And of course, they need to here use our why take NL here? Because it is a right subtree, so this is new right subtree. Okay, let's rename it a little bit. And here we have the new left subtree. Here, this is the new left subtree. And the pattern mesh this information from here. New left subtree. Okay. I think it was something like this. Why I have these red lines here? Oh, I think I forgot braces. Like this. Of course. Of course, I don't need the left and right subtrees. Let's remove these redundant brackets here. I don't need them. Okay, okay. Okay, now we have this merging function which do the merging and recalculate the sizes and the queries on our Cartesian tree. Okay. Cartesian tree with implicit k. Now let's go to split function. Split function. Split. What do they have? Of course, they have this binary tree, that these constraints, they can take it from here. And also we have some index in which we want to split these trees into this tree into two subtrees. Okay. So we need to return a pair of such subtrees. Okay. And let's go to definition. We have our tree as the first argument, and we have this index by which we want to do the split. And here we need to write definition. We can do our split using the information about the sizes of the left and right subtrees. So we have with this tree here, and of course it has the left tree and right subtree. Okay. And let's better match this tree. Constructed with some node constructor. It has some node. I think I don't need it. All I need is the left and right subtree. Actually, I need to go inside of these left and right subtrees to know the information, I think, about their sizes. So I can use the pattern matching here. So let's pattern match our left node. What do they need? We need to know the size of the left node. And I think that's all what they need to know. And the same thing with the right subtree. Okay. We need to know the right size. Okay. And here we have some cases. What if our splitted I is greater than subtree from the left, the one case, and another case if our y is Now let's start from the if our y is less than subtree from the left, the one case, and another case if our I is greater than subtree from the left. And also we need to catch one case where they can actually do the split. In this case, then our I is equal to the size of subtree from the left plus 1. Okay. So if our I is equal to the size of the left tree plus 1, this means that we can do the split exactly in this node where we now. And that's what this mean. What this mean to us. Let's at first name our left and right branches. Left and right branches. And now here we can define it as a pair which consists of this left subtree and the node itself and the right subtree defined to us the new this second element of this pair. So we can construct it with a node constructor, and we can we need to use element here itself and the right empty tree from the left and right tree from the right. Okay. And also I think we need to recalculate here the structure, the sizes and the queries of this left and right. All this first and the second tree, but let's at this moment I will focus on just structure, and then after that we will do the recalculation. Also I think I need to use sub left plus 1 here and sub left plus 1 here. So if our y is less than sub left size and plus 1, and this means that we need to do the split somewhere in the left branch. Okay. When we do the split, we will have the pair, and here of course they need to define some pair which is built from this splitted from the left two trees and the right branch and the node itself. So we have this free at all elements and we need somehow combine them to construct this pair. Let's for simplicity define them as L1 and L2. Let's define this like split from the left, split from the left 1 and split from the left 2. Okay. And go to our definition. As I said, at first we need to do the split somewhere from the left tree. So we use split somewhere in the left with our index I. And then we do this, we will have them two trees. Okay, I can call them as T1 and T2. So we need to redistribute this. So on this, I think the first element, this T1, go here, and then we need to define the right, the second split tree as a node and as a T2 from here, from the left side, and the right tree as it is. I think something like this. I think better to rename this. So here we have left split 1 and left split 2. And left split 1 go to here, and left split 2 go to here. Okay, also we have, when they go to the right, we need to do same thing. So copy this, and the split in right subtree, and they have right split 1 and right split 2. And this pair we defined, the first element, first tree is a node itself, with it left subtree, and right split 1, and the second element is the right split 2. Okay. Okay, some name clash here. Let's rename this split. How can I rename it? Okay, let's remove this I here. SPLT, that's how will be our function. Okay, I had some extra slots here. Let's remove them. And where is one point here? When they go, when they split in from the right, we don't need to use this I index here, because the enumeration from the right subtree starts from, so the right subtree contains more or less values, less nodes than the whole tree, and the I index in the right subtree will be, we need to take this I and subtract the size of the left subtree. I think something like this. And also, where is, let's return to our recalculation of the sizes and the query information. So we need to recalculate this value and this value, Q. Okay. So I mean that information about sizes and queries in the left, in this case, in the left subread is okay. It stays as it is, because we don't do any modification inside of these trees. right tree also stay, it is okay, we don't need to, but if they look at this tree, it is modified and they need to recalculate the node. So I need to define the new node here. And actually, how can we define it? What is recalculating here? So because this new tree has no this left subbranch anymore, we need to recalculate the size. So actually we need to subtract from the size of this left subtree. Okay, let's at first unpattern match this node E. So we have this node E, and I can unpattern match it as it has some size, then it has some value, it has some query, and it has some y value. Okay. Now we can define our new node E. Actually, this is our, we take our size, we remove from this size the size of the left subtree, and this is the new size. Okay. The next thing, they provide the v as it is, the value of this node as it is, and they need to recalculate the query. And actually they just take our query from right subtree, yes, because it is only used here, there is no left subtree. We can take it from here, we can mark it as query right, and we take it to here. Okay. And our y is stay as it is. Yes. Now we need to recalculate the node in this case. So let's define it like this. And what's happened here? What's happened here? This new tree, we need to remove the size of this of the left tree because they removed it, and also we need to add the size of this new left tree. So we take our previous size, we remove from it the size of the left tree, and we need to add the size of this tree, ls2. And of course they need to extract this size, I think, somehow. How we can extract it? Oh, to extract it we need to unpattern match. Yes, they need to unpattern match it from a node. How to do this? We can, I think we can do it here. We can unpattern match it as a node on which have some left and right subtrees and a node, and this node can be unpattern match like okay, this is left size tree size, okay, and I think also we need, let's think about this later. Okay, we take this size and add it to this new size. Also, we need to provide the v value as it is, and we need to provide the new query. Okay, so let's extract it from here. We have here some query result, and we use the right query result with the monoid append, and here we use this query result. Okay. And y stay as it is. And the last case of the definition, this is this node. What we have here? Here we have, by the way, I think I can simplify this thing. I can use just size of this thing as the left subtree and the size of the right subtree. So actually I think this will be more simply definition if I defined it like this. Okay, so we take the left subtree and its size and the right subtree and the new right subtree and its size, and we just sum them. And this is our value in our new node, new root node. And exactly in the same logic I can do here. I can take the size of the left subtree, and I need the size over this subtree. And to do this, I need to do a pattern matching of this element, and let's do it. Actually, I can just copy paste it from, I think, like this. But I need to provide the new names. So we have this right split 1 and size and right split 1 query. Okay, and we use this right split 1 size when the stay the same our value, and the take. Now we need to build a new query. Of course, I need it to extract it from here, query left, and then use this query left append. So this is monoids. I need to append it with this thing. Okay, I think something like this, and also we need to provide a y. Okay, I think this is all the main logic with split. I hope I don't do any errors, but later I will do some demonstration of these functions, and if I do any errors, we will see it, and we will fix it. I forgot the case. Then I want to split the empty node. What if I want to split an empty node? In this case, I need to return to empty trees. Okay. And also there is some problematic cases when we have this empty, then this subtree, left subtree or right subtree can have empty trees. So we need to catch them explicitly, I think. What if I have some, I'll take it from here. And what if I have empty from the left, like this? And I think I can remove this from here and mark it as a right subtree. What do they have? Empty a left subtree and some right subtree. But no, let's remove it from here. I think I can do it in a simpler way. So we better match it here and here. And actually we need to extract this SL and QL and SR and QR information. But let's write a function which will extract to us this information if this node is constructed with a node constructor, or otherwise, if this is an empty node, it will construct to us the zeros. We can let's name this function as extract. And what we provide? We provide some node for this. In the case of SL and QL, this will be LLL subtree, and in the case of SR and QR, this will be right subtree. Okay. And let's define the extract. Extract. When we have the empty node, we can say that the extract is 0, 0. But if we have not empty node, so something like this, we just better match our S and Q and return it as a pair. Okay, and now I can S Q, and also of course it has some left and right subtrees. Now I can remove this and pattern matching because I don't need it anymore here. Okay. Some problems. Yeah, I think it can determine the types here. And, let's set them explicitly, but why? Okay, I think the problem is the Q parameter. So I need to add as it if I add numeric q here, yes, now I can use zeros here. Actually, better not to do this, because our q is monoid, and I think it is better to use the neutral element here. So let's remove this num from here and use numpty here. Okay, now let's go to insert function. I think time to do it. So what we have? We have a binary tree, some index, and some value which we want to insert, and we want to build a new binary tree. Okay, let's do the definitions, the index, the value, and how we define it. What information I need to do the insertion? Actually, I need I need this tree, its left and right subtree information. So I need to extract the sizes of the left tree and the right subtree to make the decision on what to do next. Okay. And I think I don't need this node at all. Okay. What is my cases? My cases are if what if my inserted index is less than size of the left tree? Then they do something. I will define it later. And second condition is what if my index is greater than size of the left tree, then they do something. And one more condition, one more case, if our I is equal to size of the left subtree. In this condition, we actually do the insertion. Okay. So how we do it? We need to construct a new root node, and this root node will have some values. We need to calculate its size at first. Of course, this is the size of the left subtree plus size of the right subtree, and plus one element itself. Also, I need to provide put the value itself, and next thing is queries. Okay, I need to define query results, and to do this I need to take query left and append it to query right. Okay, and also I need to interesting that I need to append it the value itself. But value and v and q are the different types here, and I think I didn't catch that in the start of the video, and I need to fix this. Actually, let's comment this at a moment. So when they defined all these functions, they have v and q, and this is the different types. But because we use some querying on our values, we need that our values will be the same type as the query itself, and also these values need to be monoid. So, and let's fix this by just renaming this v to q, and this v to q, and this v to q. Okay, and as you can see, this do not provide any errors. And also I can change this here. Okay. And now let's return to our insertion definition. So I insert some let's add these orderings here. Constrain these constraints to types, and I do insertion into such type of the tree and provide some key value. Actually, this is the inserted value. Okay, we calculate our new size, new query result, and here we need to provide the y, and where I can get this y. And I think this y should be provided from some external source of the random data. And let's use a pair here which provide some type. So we provide a value of type q and its y random value somewhere from the external source. Okay, here we better match this thing and just use this y to insert it into the node. Okay. And left and right trees goes as it is. And actually this is wrong, because I can't just put y here, because maybe in the left or in the right some branch where is y's with some higher y, with some higher value, and then this y and this means that I need to use merging here to provide this thing. So I need to take this tree without right subbranch with just node and the left subbranch, recalculate this node and then merge it with the with this node, and then merge it with the right subbranch. Okay, and so on. But I think there is some more simpler case to do this thing, and now we will look at this. What if I remove all these and remove all these and take this tree and I split it? What if I split this tree by this index y? So with this will give me, if I split it, this will give me the two subtrees, two trees. Let's call them T1 and T2. Okay. Now I have this T1, T2 trees, which I can use them to merge it with this tree which consists only from one node. So let's create this node. This node we have only this node consists only of the one element. So this is v itself. It has value the. As a query, it has v itself, and as a y, it has y, provided y. Okay. And what we do next? It has the empty and empty right, left and right subtrays, and this is the node which we want to insert. Now what I'm doing, I'm do the merge of T1 with this node tree. After I do this, I can merge it again with T2. Okay. And this will give me must give me the correct Cartesian tree with the implicit case. Okay. And let's try to compile this and run. So I will load my file. And let's try to insert into the empty tree in the position 0 some pair, for example 1 and 2, and this fails. Okay. It fails because of naming. So let's rename it to ins and reload. Okay, another error. I need to provide the queue type. So I think I need to import monoid. Also I think I can remove some types from here. Import data monoid. Now I can try to reload. And I need to define the type of my binary tree. So this is the binary tree which contain int let's provide monoid type. We can use sum, for example, sum, and for y we can use int. So let's provide ints for our sum. Okay, now we have this tree, which of course I can print it. Okay, now I think we need to write function which takes some array and produce from this array a tree. So let's define our data as a list of pairs. And how we define our pair? We can, for example, use some x and y's, but we need to make them unique. Something like this. Now I need to define its type, and the type which I want to use is this is a list which contains the pairs. The first element of the pair is a sum of int, and second is also sum of int. So this is the monoids. Here we use the integers, and actually we look at our integers as a monoids by sum operation. Now let's define the build function, which takes some data, and it uses fold function. Let's try fold L, for example. Look at its type signature. Yes, we can use fold L with our ins function with some initial element as an empty tree, and with list, which is actually our data. Okay. And the problem here is that our insertion, it has this argument, and it is better to use it as a first argument, I think. Let's do it like this. Now let's change it like this. Okay, and now I can insert into the 0 position like this. Okay, let's try to run our build function, the d data, and we have the exception, of course. Not and has exhaustive patterns in. Okay, what is the line 57? And of course, to fix this line, I can use my extract function. Extract function. Let's use. So what we input matching here? We input matching here some tree, and we want to extract these S and Qs. We can do this like this, in a safe way. So if it is empty, then if it is empty, when they will return the zeros. Okay. So now I can remove this. And also I think I need to do the same thing for this. Okay. Let's do it. We have RS1 and RS1S and RS1Q. And now I can remove this in pattern matching. Yes? Yes. Let's try to reload and run again. And we have some tree. Let's print this tree. Okay. What do they have? Hard to read, be honest. Okay, why I use this sum here for my y parameter? I don't need it. I can use just int to this is actually the random value. Okay. So as you can see here, we have the number of nodes and it is not correct. Okay, but the second element, they have the values itself, and it seems like we present in our tree. As a second argument, they have the sum of our tree, and it is also not correct. This means that there is an error somewhere in the logic, but the root sum is correct. And as the last argument, we have our y's, and our y's, it seems that our y's is correct. So I can change the order here. For example, what if I take 5, 2, like this? Okay. 5 at the top. Well, then 4. It looks like y's are correct. And I think it is better to demonstrate with the string, not with the integer. So let's use string here. What do they have? A, B, C, and D. Here I will find it as a string. Okay. db I think one thing we need to do in this line of the split, because here I must add one because there is also node itself. So we need to remove the number of subnodes from the left tree and one node itself. Yeah, let's try to do this. Yeah, do the reloading. Save, reload. Also, I think I need to simplify this thing. Why I do it so complex? I can just use subnodes from the right. But there is some problems. So why I add this y here? I think I don't need this one, because if my y is equal to 0, what if I want to split by 0 at 0 point? In that way, if I have no nodes from the left, so this will be 0, this will be 0, this will be 1. I will never go to this case if y is 0. So let's remove and try it. As it is. Okay, I think I found the problem. We have some mess here, I think, in the merge function. For example, here when they define the new root, if y1 is greater than y2, when they construct the node, with L1 and NR2 new right tree. Left one stay as it is, and here we need to have this size as a sum of this size subtree and this size subtree plus 1. But I use something missing here. I think I do the mistakes, and now let's fix them. And the first thing I want to do is to, so actually I can use this extract function. I will put it here because it is used, can be used also inside the merge. Okay, and now how I define the new S1 and S2. So I need to extract from left one this parameter and take first of it. And then I need to also take the first of this right subtree, new right subtree. And this is S1, new S1. For S2, I do exactly same thing, but I'm using this trees. Okay. For Q1, they're using exactly same logic, but they use here append operation, and here I extract second element, and exactly same thing here, but with this trace. Okay. Now let's try to recompile again and think again. I think there is some errors. Go. And nothing changed. Also, I see that how I define this new node is. Why I'm using just sub right. Okay, I of course I need to add one here because the node itself has the element. Reload. Now it became to count, but okay, it count okay here, it count okay here, but here okay, but why here there is only two? Okay, I need to think. And I do the same error here, I think. Oh. Here because I'm yes, the node must count itself also, but here I am only counting the subtrees left and right. Okay, let's try to run now. Oh, okay, it start to count. So we have 4 in the root. Yes, we have 3 here. And we have 1 here, 1 here. It is okay. 1, 2, 3. This 3 we have 3, and this 3 we have... Okay, but and it's look like it is okay by y value, and the order is D, C, B, A. So and it's looks like the order of its insertion looks like works, but we need to check this more deep look at this a little bit later. And I see now one problem, that it doesn't calculate to me the query, correct query. And the problem with monoid, I think it is exactly the same as I do. It's exactly the same mistake that I do with the sum. So why I use only For example, here, why I use only left and right subtrees? I need to use the element itself. And in this case, the element itself is v1. So I must put it here. And here is element itself is v2. Okay, this is one place where they need to fix. Second place where they need to fix this place. Here we have the element itself, and they need to put it here. Okay, looks nice. Let's check how this works. BAMS and work it or not. Oh, one point I forgot here. We need to also use our element here. Let's reload and let's run. Looks like true. So we have here C, and here we collect our DCB, and here we collect our DCBA. So now it looks like that it works as I expect. Okay, now let's try to. Okay, I have this BD. So now let's mark this tree as T, and let's reload. Oops, what I'm doing wrong. BD is a function. Okay, let's define T as BD. Okay, like this. Let's print our tree. And what if I want to insert into position, for example, 1 of this tree? I want to insert some new pair which will have, for example, X and 5. Okay. Oh, non-exhaustive patterns in the function merge. I didn't catch something. Or I provide some wrong data. Yes, of course, I provide some wrong data because it's duplicate. And I assume that we have no duplicates. 6. Okay, if I put 6, we have some tree. Let's print it. Print this tree. As you can see now, I have this new inserted X at position 1. So we have this 0 position, this 1 position, and so on. Okay. Now let's implement some in-order traversal function on this tree to show the correct order of our tree in a nice way. This will be useful, I think. So I will call this function in-or, and what it's take? It's take this binary tree, Cartesian tree, our Cartesian tree with implicit k, and it's produce of a list of such elements. Okay, and how we define this function. So let's unpattern match our node here. If we have a node with some element inside and some left and right subtrees, what we do at first? At first we do in order from the left when we add our element itself, and then they do in order to the right. Okay. And let's catch the empty case. In the case of the empty tree, of course, we have the empty list. I'm not care about performance of this function. I don't want to do any tail call optimizations. I just want to look at my trees as arrays, as a lists. Let's try to reload and run our in-order function for our tree. And you can see here we must look at so at this position. This is our elements. We have D at position 0 because D was inserted as the last element of our folder into position 0. When they have C, then they have B, and then they have A. Of course, actually, it is better for me to do why I do this order. This is not readable in the array because I have these sizes, so it's better to remove this. And actually, I think we can do this a little bit if we modify our type signature. Let's do it, I think. Let's modify. Let's remove our int. I think we don't need it. We don't need the query data, and we don't need y, because why we need it if I want to represent it as an array. Okay. And here we just need to pattern match our values. Exactly, we need only one value. We don't need others. Let's do it. Now, as you can see, we have an array as a result. Our tree represents a list or an array. Also some sequence of values. And we can use this to check the nice visualization of our trees. Okay, let's for example now insert in our tree. Where is our insertion? We need to insert, for example, what if I want to insert in position 2, in our tree, some pair with x and with 6 as y. Okay, I think that's enough. We have some tree, and now I can in-order this tree. And what you see, we have inserted in. So we have 0, 1, 2. And after the position 2, we insert our x. 0, 1, 2. But actually, I think there is some problem in our insertion, because what if I insert to 0? Okay. No, it works open in 0. It works ok with 1. It works. And you can see the 2, why it's inserted. I think there is some error. And what if I insert as a 4? As 4 it is okay, but as 0, 1, 2, 3, no, it's not okay. There is no 4 at all at our list. 0, 1, 2, 3. So again, we have this initial tree, and then I insert into position 2. I actually received not inserted in position 2, I received the insertion into position 3. And I need to know to find why this happens. After few steps of debugging, I found there is possibly the error. So here I forgot the braces. So of course I must subtract the left subtree plus one plus the element itself in the node in which we now in our position. And I forgot these braces, and that's give me an error. So let's reload and let's do some insertion. Actually the error was in a split, so let's check a split the different parameters. For example, I will split by 0 and take the first element. So now I must to get the empty list because the 0 and all other part go to the right to the second list. Yes, as you can see, it correct. Now let's check second the list itself. What if I split by 1? Okay, I get the correct second and correct first. What if I split by 2? Okay, I get correct first and correct second. What is if I split by 3? I get correct second and correct first. And if I split by 4, 0, 1, 2, 3, I get correct first and I get correct second. And we can now check our insert. Where is our insert? Okay, here. What if I insert into 2? 0, 1, 2. You can see the X inside the 2 position. What if I say it's insert into the 0? Now you can see it is in 0 position. What if I insert into 1? Yes, it is in 1 position, into 2, into 3, into 4, into 5. If I insert into some position which is greater than the whole list, it is just inserted into the end of the list. So actually you can see now where they have Cartesian tree with implicit k, which acts like a list, and this insertion is done in logarithmic time. Okay. Now let's write some very simple function which can be very useful. For example, we can write function like a size, like a len, which will return to us the length of our array. So array, but actually this is not array, this is the tree with implicit k. But we can very easily do this function. To do this, we need just to pattern match our tree. We do not need left and right subtrees. They need to just extract the size. Okay. If they extract this size, we can return this size. Of course, this is when our tree is not empty, and if our tree is empty, then we return the 0. So let's reload and check the length of our tree. As you can see, the length of our tree is 4 elements. So I'm talking about this tree. Now we can implement very easily two functions which do insert to the first element of our list and into the as the last element of our list. So we can name them insert first. What do they need? We can use this type signature from here to do the insertion. And how we did it? Insert first. We have some tree, we have some pair, all the value and all the y, and they need to do the definition here. So we can use our merge function, of course. We need to merge the node tree. So we need to create at first the tree with only one node. We can name it as T1, and I want to merge this T1 with my T. Okay, and let's define our T1. We will define it as a node which contains from only one element, the v itself. The query result is v, of course, and the y is our provided y. And it has the empty left and empty right subtrees. Okay. And here the I think merge dictates me that I need to have monoid. Okay. And ort. So we use a merge, and merge, as we can see now, where type signature have this constraint, and that's why I need them here. Okay, let's check our function insert first. What if I insert first to our tree some pair with 11 and x, so I need to provide uniquely random wise. Open. What's the problem? Oh, okay. I think I changed the order of pairs. I needed first to provide the value itself and then the y. Okay, and let's print it as a tree. As you can see, it works. It's insert me in the first position. Exactly in the same way I can do the insert last. So we can insert last. The difference only in the order of these operations. So when I do the insert last, I must at first merge tree itself, and then the second argument will be my one node tree, and this gives me the correct result. Let's look insert last. What I'm doing wrong? And I'm doing wrong that I'm not provide the argument. Okay, you can see it inserted into the last. So it works. Insert first, insert last, they works. They have length and all this function for logarithmic time. Okay, now let's do the delete function. Del function. This function will delete, so we can use this type signature and provide some index in our list. There we want to delete our node. And as a result, we will have this binary tree. Okay. How we can implement this? We need this tree as the first argument. As a second argument, we need our index. And the idea, of course, is to use the split. So at first we will split our initial array in the position. Then we want to delete this element, and then after that we will have two lists. One of them, first of them, represent the elements before this position, and the second list will represent the elements after this position, and the element itself also will be in the first position of the second list. Then we can take this second list and split it again at the first position. And then we take a second result of this split and merge it with the first result of the first split. Okay, so actually we do the merge of T1 and T2, and they need to define our T1 and T2. So what we do? We do the split. For split, they need to provide. Where is our split? SPLT. We need to provide binary tree and the int. So we provide our initial tree and the int. After that split, we will receive our T1, which we need to merge at first, and then we will also receive some tree. I will call it temporary tree, TT, and from this temporary tree we split the second part. Okay, so I think like this. I think like this. Okay, let's add monoid and ordering. Okay, and I think we done. We can now test it. So let's reload this our T. this our t. And what if I want to remove from this t the position, for example, 1 position element in first position. So this will be remove the C. I expect this. Yes, and it's remove C. Of course, I can remove 0 position and second position and last element. Yes. If I remove, if I try to remove the in position which is not in my list, then they have then our list stay as it is without any modifications. Interesting that we can implement the interesting function, the del range, and this function will delete the whole range in the array. Okay. So we can use exactly the same type signature for this. And one modification that we need to provide the second argument for our range. So our range is defined by 2 integers. And how we will implement this? So I have this tree. I have this start position of the range A and last position B. And what we do, how we implement it. So we can take our initial tree and split it in the A position, and the left part will go to our result. Also, we can split this tree by the B position. And when we take the second part of this split and split it in position 1, we remove the B element itself, and we have the last part, and we merge them. So actually we do the merging of T1 and T2, and we need to define this T1 and T2s. So how we define the T1? To define the T1, we will define it like do the merging, so split of T in position A. Okay, this will give me the T1. The T2, how I will at first to get the T2, I need to split my tree at position B, and this gives me what this gives me. This gives me some tree which I'm not interested in and some temporary tree. And then if I split my temporary tree in position 1, I will get the T2. Okay, let's check. We have our tree, and what if I want to delete from 1 to 2, for example? Del range in my T from 1 to 2, and yes, as you can see, I will output this my initial tree. And what if I remove the from 1 to 2, I remove the CB interval, and it gives me this new array. Of course, I can remove from, for example, from 0 to 2, or from 0 to 3 the whole list, or from 2 to 3, and as you can see, this works. Okay, let's check some corner case. It will work also. And interesting that we will do this function into logarithmic time, because we just use the merge split here, and we all work in logarithmic time. So, but in the case of array, this will be a linear time if we use the array list. Let's implement also the function which will get to us the element in some position. So we can use this type signature for this. If I provide a binary tree and position, and I want to return the Q. Okay, and let's add constraints. We have tree and have index, and they can do the definition. So how can I get it? If I take the tree and if I do the split in the I position, when my element will be at the second tree as the first element. When if I take this second tree and split it in the one position, in position 1, this element will be at the first the first result of the split will contain only one element, and this will be this element. So I think I can return the not just Q, I can return all the node, all the information. But let's for simplicity return just Q. So what we're doing, we need here I have some body definition. I will skip it for a moment, but what I need to do, of course, is to split my tree at position I. After that, I have left. I have two trees. I'm not interested in this tree. I'm interested only in this tree, and the second tree. Well, then I do the split of this tree in position 1, and now I'm not interested in this tree. I am interested in this result tree. After that, what I need to do, I need to better match this tree. Yes, I need to better match this tree, and actually I need to extract the Q. Okay, so I can define a function for this extraction. I think I can write it as a x extract, and this function takes some tree. Here we can say that we can find this element at this position, and there is possible way that user provides to us the position which is not in the list. And in this case, we can't return it. So this we have this maybe here. And in the case if our extract function run the empty tree, called the empty tree, so not called, we are this is functional paradigm, so we can say that applied, our function applied to the empty tree, we can say that we can return nothing in this case. Okay, but if our function is applied to some tree constructed to the node, be interested in some element of this node. So we interested in we're not interested in the first element, we interested just the value. Value is the second element. Okay, we're not interested in this element and in this element. And we define this function as v. Okay. Okay, and here I defined my function is the extraction of rt. Okay, I think like this. What's the of course I have a SPLT function. Oh, here I need to provide just. Okay, let's try. We have this tree, and now let's try to get d0. We have just d, t1 just c, t2 just b, and t3 just a, t4 is nothing, and so on. Oh, why it's taking me for -1 d? Very interesting. Of course, it does make sense to use negative indexes here, and I think I can use some guards here. So, for example, I can check here that if my I, so here I have overrides, and here if my y is less than 0, when I can I think I can run, do the error, or I can just return nothing. Let's reload, and let's try. So you can see in this case we have nothings when they're not in our range, and it works. Okay, and in the last, let's do function which do the query of the range. So we'll call this function query. Okay, what it takes, let's see from here. We need to provide the binary, the Cartesian tree, the implicit key, and we need to provide the range. And in this range, we will return the query, the monoid query. Okay, we have this tree. we have start of the range and end of the range. And how we do the definition. At first, I will take all my list, which represented this t, and split it by a. After I do this, I'm not interested in the left part, I'm interested on the right part. I will take this right part and split it by b minus a plus 1. And that part of this split will give me the tree which will represent for me this query. And then I will take the root node and extract the query result from this tree. Okay, let's implement this. So, as I said, we have some definitions here, and I need some data which I will receive from, I will do the split of this tree in the A position. And I'm not interested in the left part of this tree, I'm interested only in the right part of this tree. Okay, let's call it TR. Now I do the split of this TR in the position of b minus a plus 1. After that, I will receive tree. I'm interested in the left part of this tree, so I'm not interested in the right, I'm interested in the left tree from the left. And I need to extract from this tree from the left the information. Of course, if I will provide a function for this, if we have empty tree, so if I will give some query which is inside, not inside my binary tree interval, I need to return nothing, so I also must have maybe here. And let's return nothing in this case. But if I have some tree, like so we can take this code from here, but we interested not in the value, we interested in the query, and we return just query. And we do the extraction from the t left. Okay, t left. Okay, if I don't do any errors with these indices, I hope so. It must work. Let's check this. Range, we have this tree. Let's show it, and let's show it in like a tree. And what if I want to query what if I want to query the result from C to B? So this will be from 1 to 2, for example. What if I will take the range of this tree from 1 to 2? Yes, it gives me CB, as you see. So, and from, for example, 0 to 2, we have DCB. And from 0 to 3, we have all the string. And from 2 to 3, we have BA. Yes, as you can see, this thing works. If I give incorrect interval, it gives me all possible. So that's okay, yes, why not? if I give from 0 to 1, and if I provide minus, so let's check like this. Okay, with minus, so with the negative, it gives not correct results, because as I said, negative is something that is not acceptable in this case, negative indices. Okay, let's call the error in this case. So I will use some guards here. Here we will have otherwise condition, and here if our a is less than 0 or b is less than 0, or we can also provide that our b is less than a. This is also not very good. Well, the we'll call let's define it's like nothing. I don't want to provide errors. Yes, in this case it works. Okay. So of course we can use any monoid here. It can be a sum or minimum or maximum. So let's demonstrate this. If I take these data definitions and put it here, and now if I will use I can use numbers, for example. Use numbers here. What if I provide some, for example, 10, 12, 30, and 40, and this will be the integers. Actually, monoidal sum. We can use monoidal sum, for example. Let's reload. Let's in order our tree. We have. You can see they have this our data, and now I can query using my monoidal structure. I can use query sum. So in the previous case we have the strings for our monoid, and now we have the sum, and I can run on this tree, for example, the sum from 1 to 2, and this give me 15, as you can see. If I run from 1 to last element, this gives me 16, and I can also run it for all the elements. This is 100. So we can take any subrange in our array, and it works. And this is very abstract. We can change this very easily in this type to a minimum, maximum, and so on. Any monoid can be used here. Okay, let's comment this, and we go back to our strings. Now, what I want to do, we have insert function. Let's implement also the set function. So we have get, we have del, We have del in the range, but let's implement the set function. How it works? It works like the insert, but it doesn't shift the right part of the array. There the insert, it just change the value in some position. And of course we need to provide this value like we do in the insertion. Here we need to provide it. So we provide tree, we provide position, and we provide the pair which we want to insert, and we return as a result the new tree. Okay, we have this tree, we have the position, we have the value and the y values, and let's go to definition. So actually we can do this using the del function and the insert function. We have this del function, we have this ins function, and we can use them. So at first I will delete the element in this position yi, and then I will insert the element in this position y. So actually we do the insertion into some new tree in which we do deletion. We can call it delete tree. What's the steps we should insert? Yes. At first I need to provide the integer, then the tree, and then the pair. Okay. I provide the integer, then the tree, and then the pair. Actually I can name it as a p pair. P. And one thing I need to define here is our D tree. What is a D tree? Actually, D tree is a tree which can be defined as delete, applicable to our 3T and our position. Okay, like this. Like this. Okay, it tells me that I can use at reduce, but I don't want to use it. So let's reload. Let's show our array, and let's try to set to position 1 some new pair, for example. So for example I want to set x with the y11. Oh, so where is our data? At first I need to provide x and then 11. Okay, set. Okay, I need to of course provide a tree. Why I don't provide it? I provide it, and let's check the result. Yes, as you can see at the first position our c changed to x, and I can for example set all the other position, for example 0, 1, 2, 3, and our x go to this position in logarithmic time. Oh, I can insert in the last position also. Okay. Now we have the set function. Okay, all these functions works for logarithmic time. Of course, in the array we can set the constant time, but all of these other operations will be not in the constant time in an array or in a list. So we have set, we have get, delete range, insert, and we can use it as a static tree or segment tree with this query function, very interesting. So this is a very nice data structure. All for log n. This is not all the set of the operations which can be done with this data structure. Maybe I will do some additional video. Video number 2 about this data structure, the Cartesian tree with the implicit key. But for today this is all. Thanks for watching. Push like, push subscribe, write comments, and see you in the next video. Bye bye.